All right, let's talk about this little thing they call atomic mass. So we know where it comes from, the protons and the neutrons. But what does AMU stand for? How do they get these numbers? Why, when you look on the periodic table, does it have those crazy decimals for the masses? So to start off, the atomic mass, AMU, stands for atomic mass unit. So, they couldn't really measure it in grams or even milligrams because atoms are so tiny. And if they were to use the scale using a gram, it'd be something like nanograms, and it would still be like a tiny fraction of one of those. So instead, they came up with a new scale, so a new unit to measure the masses of atoms. And what they used was the AMU, the atomic mass unit. So they took carbon-12, they took a carbon-12 atom, and they set that as 12 AMUs. And then everything is relative to that. So something that weighs twice as much as a carbon-12 atom would weigh 24 AMUs. Something that weighs half as much would weigh 6 AMUs. So it's all based upon that little piece right there. And we talk about like carbon-12, carbon-14, hydrogen-1, hydrogen-2. But when you look on your periodic table, you see these decimals, like hydrogen is 1.0079. So where do those decimals come into play? Well, the masses on the periodic table are the average atomic mass, and they're based upon the relative abundance. So the atomic mass given to you on the periodic table is an average of all the isotopes of that element in the world. So the average mass of any large number of atoms of the element is always the same for that given element. So the ratio of isotopes for each given element is a constant. So that means that the number on the periodic table can be used in stoichiometry. So if we know we have 5 moles of carbon, as long as it's a large sample of carbon, we can assume that it's going to weigh the 12.011 that it says on the periodic table per mole. And so we can use that then to do calculations. So even though the sample of carbon might have carbon-12, carbon-14, even carbon-16, carbon-11 mixed in there, because the large quantity and the average, the ratio is constant, that means we can do calculations to figure out what the mass of that sample is. Or from the mass of the sample, we can figure out how many moles there are. And the mass, the average, isn't really based on kind of your same math average where you add everything up and then divide by the number. Instead, it's based upon the relative abundance. That means carbon-12 is the most common version of carbon, and so it weighs heavier. That's why the average ends up being 12.011, because since carbon-12 is so much more common, they weight it heavier in the average. Mass spectrometry. That is a cool word, and we're going to learn what it is. So to get those masses on the periodic table, like we said, atoms are tiny. It's not like you could take an atom and drop it on a scale and say, that weighs 12 AMUs. So instead they have to use different technology to figure out what the mass of an individual atom is. And that is this device right here, which is as cool as it looks. So what they do is they take a pure sample of an element. So they would take a pure sample of carbon, pure sample of aluminum, iron, any element that they wanted to test. And they would ionize it by running high-speed electrons through it. What those high-speed electrons will do is they'll actually take electrons from it and turn this sample into an ion. Okay? Remember, an ion has a charge, so if we're doing this with carbon, run those through, we end up with a carbon with a plus charge. Then they can shoot that beam through this electric field ion accelerator. So acceleration is speeding up. When you push the gas on your car, you are accelerating. And what this does then is it takes those ions, since they have a charge, and it accelerates them through a known acceleration. So we end up giving ourselves an acceleration, that's A, and then it flies through really, really fast and comes to this magnetic electric field, and there's a positive and a negative there. So what this does is, since those ions have a slightly positive charge, and that's because the electrons that they flow through them, they rip off the other electrons, leave it as a positive charge. So it's going to be deflected away from this positive plate and attracted to that negative plate. So then what happens, as this is flying through at an acceleration and it comes to this and it's pushed by that positive charge, imagine something going past you and you pushing it as it goes past you. When you push it, it's going to get deflected from its path. So instead of going straight through, it comes slightly deflected down. If something really lightweight comes past you and you shove it like a small child, you're going to deflect it really, really far. So like this beam right here would be from a smaller isotope, so a lighter isotope. So that positive field can push it and shove it down a lot farther. Whereas let's say a car drove past you and you gave it a shove, you wouldn't deflect it very far from its course, and so as a result it wouldn't deflect as far. So then they can figure out, based upon calculations using acceleration, mass, and Newton's law, so force equals mass times acceleration, they can use where they strike and how often they strike on this detector plate to calculate then the mass of those particular atoms. The distance between where they strike is going to be proportional to the difference in the mass. So they can measure that distance where they strike on the detector plate, and they can use that then to calculate out its mass. Okay. This concept right here, you guys, spectrometry especially, is something that's actually being pushed very big on this year's AP test. So try and really understand what's happening here. I'm not just telling you this for interesting facts. You do need to understand spectrometry, and this is something that you might need to explain on a test, how this works. So here's something you're definitely going to see on the AP test, and this deals with the spectrometer data. So when they run one of those tests where they're shooting that beam and those ions, knocking them off course, getting the mass, this is kind of the readout, so the graph of the data that you would get. Now, remember how I said that the masses, they're not always the same, so it's not just a straight up average, because like carbon-12 is more common than the other ones. If you look here in sulfur, you see that we have these numbers on top, so 51.84 and 48.16. If you add those two together, you see that it equals 100. And that's because those numbers are actually percents. So 51.8% of the strikes were at silver 107, and 48.16 were silver 109. That means in a pure sample, 48.16% of that sample is going to be silver 107, and silver 109. 51.84% would be silver 107. Okay, so this question wants us to find the mass of 107 silver. Now, I know what you're probably saying, well, it's 107, it's written right there. No, they want us to find the actual mass, so give us some decimals, all of that. Let's go a little more accurate than just 107. So to do that, there's a little equation. Alright, so I'll try and navigate this with you. This equation says isotope mass number 1 times the percent abundance of that particular mass. So this would be, in our particular sample, we're talking about silver 107 and silver 109. So this would be the mass of 109 and times its percent abundance. And then add that to the isotope mass number 2. So this would be the mass of 107 times its percent abundance. And what that gives us is the AMU, so the average atomic mass. So this would be the number that appears in the periodic table. So when they do one of these mass spectrometers, they would get the different isotope masses, they would multiply it by the percent abundance, so the percent of the blips that would hit on that screen, add them together, and then that would give them the number that they would then put on the periodic table. So we know the percent abundances for both of them. If you look back at the question, we would see that they said silver 109, its AMUs was 108.90476 AMUs. So let's plug some numbers in. Okay, so I took that mass, the 108.90476 AMUs, that's the mass of isotope 1, and I multiply them by its percent abundance. Notice how I took it out of percent form, so instead of saying 48.16, I put it into fraction form, so 0.4816. Now let's do the similar thing on the other side. In this case, we do not know that isotope mass, and so I'm just going to call it 107 Ag. Okay, because we're going to try and find the mass of that isotope. But we do know its percent abundance. Its percent abundance was not in percent form, but in decimal form, 0.5184. Okay. So we multiply these two numbers, then divide by that one to solve for the mass of that guy. And we would find that the atomic mass units for silver 107 is 106.9 AMUs. Which rounds up to 107, so that does make sense. You won't get numbers that are really far off of the original. Alright, here's one. I want you guys to, after we read through the problem, pause the video and give this one a shot yourself. It's the same equation, so use the mass spectra data below. There's a similar graph. It gives us the percent abundances, tells us the different isotopes, the 35 and 37. And it wants us to find the average atomic mass of the element in question and then identify what the element is. So you have to look at our periodic table to do this. The exact mass of the isotopes are 34.969 AMUs and 36.966 AMUs. And we can figure out which goes with which. So 35 would obviously be the 34.969, and then the 37, the 36.966. So using those percent abundances and the actual atomic masses of each of those isotopes, find for me what the average atomic mass is, so the number that would appear on the periodic table. Pause the video, give this a shot. If you're stuck, resume it, and you can follow along. Alright, so I took the data from the graph and from the question, and since the mass of isotope 1 is 34.969 AMUs and its percent abundance, so the letter or the number that was above it on the graph was 75.78, put that into fraction form, 0.7578. So it looks like a larger percent of this particular element is this mass or this isotope of 35. And then I took the other AMUs and multiplied it by its percent abundance. So just multiply both those, add them together, and the atomic mass that we end up getting is 35.45 AMUs. So if you grab your periodic table and kind of scroll along till you find the element with that mass, you will see that it is chlorine. And this is true to life. So these are the different isotopes that would exist of chlorine. They would weigh 34.969, 36.966. And if you just add those two together straight up and then divide by 2, like you would normally find a mass by doing, you would see that it doesn't equal 35.45. You have to take into account the relative abundance. So the fact that this is more likely to exist than this plays a role in what the overall mass is. So the two problems that we've looked at so far, they only each have 2 different isotopes. In all actuality, there could be several, 3, 4, 5. This equation would still stand the same. You would just add the isotopes. So isotope 1, isotope 2, isotope 3. You do it for as many different isotopes as there are. Okay, formula and molecular weights. Both of these are really familiar to you. We just normally don't say formula weight, especially in general chemistry, but it's something that you have to be aware of now. So formula weight usually refers to the basic unit in a network solid. So ionic solids like, let's say, sodium chloride. There's no such thing as an individual element or individual molecule of sodium chloride. You wouldn't find it, just one NaCl. Instead, when you look at a salt crystal, what it really is this crystalline pattern, repeating pattern of sodium and chlorides. So it looks something more like this. You have sodiums and chlorides. The chlorides are negatives, the sodiums are positive. So the positive sodiums would be attracted to the negative chlorides, and you end up with this repeating structure. So I mean, this could keep going on depending upon the size of the structure forever and ever. But what holds true for this entire structure is that the ratio is 1 to 1. So even though in this particular picture there's 5 sodiums and 5 chlorines, we wouldn't call this formula for this structure Na5Cl5. Instead, we just say NaCl because the overall ratio is 1 to 1. So ionic solids typically is the way they are with this. They're network solids, so we just look at the ratio of how they stand. So every 1 sodium for every 1 chloride. And then we would refer to the mass of sodium chloride, which is roughly 58.5, if I'm remembering it correctly. We think that that is a formula weight. So it's the same basic idea. You add the mass of sodium, you add the mass of chlorine. You guys know how to write ionic compounds. You know how to get their masses. Just refer to them now as formula weights instead of molecular weights. And what a molecular weight is to refer to a molecule that can exist independently. So something like carbon dioxide. Okay, there is no network solid of carbon dioxide molecules. They exist independently. Inside of water, it's H2O, and those H2O molecules are independent of each other. They're not really surrounding. It's not about a ratio to figure out their mass. So the formula weight of magnesium hydroxide. Magnesium hydroxide is an ionic solid. It's not really one magnesium, 2 hydroxides, that's it. It's magnesium surrounded by hydroxides, which are surrounded by magnesiums, which are surrounded by hydroxides, and it keeps going on. The difference is, unlike sodium chloride, they exist in a 1 to 2 ratio. For every 1 magnesium inside that structure, there's going to be 2 hydroxides. So then we just consider that one formula unit. So 1 magnesium atom, we can get its mass, we can get the mass of the 2 oxygens, the 2 hydrogens, and then add them together to get the AMUs. And then the mass percent of an element in a substance. So the mass percent is the number of atoms of that particular element times that element's atomic mass. So if we were looking at oxygen, you would count the number of oxygens. Like in the magnesium hydroxide, there was 2 oxygens. You would multiply it by its atomic mass, so 15.99, divide by the overall mass for the formula weight for the entire compound, so the entire magnesium hydroxide, multiplied by 100, and that would tell you what percent by mass of that element is the oxygen or magnesium or hydrogen. What the by mass means is we consider weight. So if you think of something like hydrogen, okay, there's 2 hydrogens, but there's only 1 magnesium. And so if you were to just do a straight up percent hydrogen, it would seem like there should be more hydrogen than there is magnesium. But since magnesium is so much heavier than hydrogen, hydrogen is so stinking light, it has a smaller mass percent. So we're going by the mass percentage, not by the number of atoms. So if we look at the mass percent of hydrogen in water, so water, H2O, that means there's 2 hydrogens, 1 oxygen, but we want to look at its mass percent. So then the mass percent of hydrogen would be equal to 2 hydrogen atoms, that's not 2 atoms, that's 2 H atoms, times its atomic mass, so the mass of 1 hydrogen atom is about 1.01 AMUs, divided by the total mass, so that's 2 hydrogens plus 1 oxygen, 18.01 AMUs, multiply it by 100, and we would find that the percent by mass of hydrogen is 11.2%. So 11.2% of water is hydrogen. Alright, here's one I want you guys to try. So the mass of hydrogen, percent mass of hydrogen in hydrogen peroxide, which is H2O2. So pause the video, give this one a shot. When you're ready to check your answer, go ahead and resume. Okay, H2O2, its mass overall would be 34.02, and we would still have the same mass of hydrogen at 2.02, because there's 2 of them, and 2.02 divided by 34.02 would give us a mass of 5.94. So a smaller percent by mass of hydrogen, that's because we've increased the oxygen, and so it's going to downplay hydrogen's role in there a little bit. Okay, so John Dalton again, who we talked about a couple of videos ago, also came up with this idea of law of multiple proportions. So I'll try and put this simpler than it's written. So when 2 elements form more than one compound, the different masses of element A that combine with a fixed mass of element B can also be expressed in a small whole number ratio. And the small whole number ratio tells us how many times more A is contained in the more massive compound. It must be a whole number, as compounds can only be built out of whole atoms. We know how to find the empirical formulas based upon percent abundance or percent of each element by mass. All this is doing is explaining why that is. So if we know the percent by mass of each individual element, we can figure out what ratio each one has in the overall atom or overall molecule, and then we can use that to write a formula. And what we see from that, what he's saying down below, is that it's always going to be whole numbers because it has to be built out of whole atoms. So you can't have something like H1.50 or HO2.1. It always has to be whole numbers. You can't have fractions of atoms because you can only build molecules out of whole atoms. And so those masses have to equal up a whole number ratio. If they don't, then calculations are wrong. And this was proven because they would do several experiments. They tested this many, many times, and you would always wind up with this fixed whole number ratio of element A to element B to element C, D, however many there are in the compound. Okay, if we take some look at some data real quick then, we can look at the masses of oxygen and hydrogen in water and hydrogen peroxide. We see that the mass of oxygen in water, since just one of them is 16, and in hydrogen peroxide is 32. And then in both hydrogen peroxide and water, we have 2.02 AMUs for the hydrogens because it's always H2. So then if we set up a ratio, so we look at the mass of oxygen with respect to hydrogen in both of them, we would get these numbers right here. So 16 divided by 2.02 and 32 divided by 2.02. So that tells us a ratio then of oxygen to hydrogen. So if we take those two ratios and we divide them by each other, so we set up a ratio to the ratios, we would get 2. So what that 2 tells us then is that hydrogen peroxide should have twice as many oxygens as water. And when you look at the formulas, or what we accept as the formulas, we see that that's true. So keep in mind, it seems kind of roundabout that I'm just proving that this is a 2 right there when we can look up there and see it's a 2. We've never seen a water molecule. We've certainly never seen a hydrogen peroxide molecule. So all of this has to be proven other ways. We accept this as H2O as water and H2O2 as hydrogen peroxide, but we don't know the facts, okay? Because we can't see those individual atoms, so instead we have to prove it other ways, or we have to verify this other ways. And this would be an example of how we do it with this law of multiple proportions, looking at the individual atomic masses, and then setting up these ratios to give us the formulas. Actually, the same thing ends up working if we do it with the masses. So if we divide the percent by mass of oxygen in hydrogen peroxide by that in water, that is the ratios of the 2 mass percentages, we would find, once again, it's 2. So this tells us that H2O2 has twice as many oxygen atoms as water does. Okay, let you guys read through this on your own. This is just kind of a wrap-up to this entire lecture. So it just talks about how we got those different mass ratios, why they're important in our calculations, and the numbers that show up on the periodic table and other places as well.